And it's my great pleasure to present my good friend, good researcher, Professor Dmitry Ryabogin. He is originally from Rostov State University, but a long time he lives in the United States, works in the United States, does very good mathematics. And thank you very much, Professor Ryabogin, for agreeing to deliver a talk at our seminar. And please go ahead.
Okay, I would like first of all to thank Alyosha Karapetyants for everything, and he's my close friend for a long time already. I'm familiar with him more than 30 years, and even I took the course of harmonic analysis from Nikolai Karapetyants long ago. Okay, so I'm going to speak today about a homothety conjecture. Let me write it like this. Conjecture on the plane. Well, let me write on floating bodies. Let me call it like this. And I am going to speak today mostly about the plane case, so we are going to live in R2. And the conjecture was formulated first by Carsten Schutt and Elizabeth Werner. It was about 1990 when they formulated the question. And at the beginning, I'm going to formulate the question heuristically, and then I'm going to formulate everything precisely. So assume that you have a convex body. A, let's say, on the plane. Well, just a second. Let me move this thing here. A on the plane. And the body is of constant density. Think that this is physical. Yes, constant density. In a moment, I will define density and everything. Constant density, and you submerge it into water. Okay, let's say density less than 1. Let's make it less than 1. Where to put it? Somewhere here. Less than 1 into water of density 1. Okay. And for simplicity, so if this is my water, if this is my body, so for simplicity, let's assume you can also think three-dimensional if you want to. So for simplicity, what I'm going to do, I'm going to fix the body and change the horizon. Okay, because this is easier to draw, so I'm going to draw horizons of water surfaces like this. Okay. So what I'm trying to say, so assume that I submerge the body in all directions, and there is a dry part. There is a part that always stays dry. I'll call this K delta. So K delta, well, KD maybe at the beginning. Just a second. KD is the part that always stays dry. And it looks like this, something like this. And D is the density. Some number, let's say between 0 and 1, fixed. And assume that you are lucky, no matter how you submerge it, there is a constant lambda positive, such that lambda times K is KD. So the part that always stays dry is proportional to the original body. Then the question is, does it follow that K is an ellipsoid? And what we are going to do today, we are going to show that the main result, this is what I'm going to present, that no, there are densities for which this is wrong. This is not true. The full picture is open, so I may not give you an answer for which densities it is correct, for which is not, but There is a lot of investigation going around this problem, but in general, in this formulation, this is wrong. Okay, now let me formulate everything precisely. So I'm going to speak about the body. What do I mean by the body? So please think that K is star-shaped with a continuous radial function. I'll recall in a moment what the radial function is. Okay, radial function rho k. And in this talk, we are going to identify, we will identify the bodies k and their radial functions. Okay. So what is the radial function? So if I have this star-shaped set, something like this, star-shaped with respect to the origin, always. So this means that if I look at the unit vector theta, this is a unit circle centered at the origin. So then I just walk in this direction till the boundary, and this is my radial function, rho k of theta. So let me define it precisely, rho k of theta. This is maximum of lambda positive such that lambda theta belongs to k. This is the definition. So basically exactly like in differential geometry, if you're here, you go to the boundary. In this direction, you go here. In this direction, you go here, etc. Okay, very good. So now the water, I'm going to write like theta in t. T is a positive, t is a real number. So the water is going to be, as usual, all x on the plane such that the scalar product is t. For some t, this is the dot product. Okay. And this is x dot theta. And I'm going to also to define the half spaces. Okay, let me define them plus, the half space plus. Plus is going to be greater or equal than t. And also minus is going to be less or equal than t. Okay. And then so fix your favorite density number d from 0 to 1. Please think that, again, because the body is of constant density, so think that d, this is just the volume of the underwater part. In a moment, I'll make a picture, divided by the volume of k. So this is the volume, the area, if you want, of the underwater part. Everything I say could be done in all dimensions, except the proof. Okay, the area of the water part, underwater part. So let's make a picture. So this is my k. For simplicity, I'll draw convex because star-shaped is difficult for me to draw. So something like this. So I have a water here. This is my water. And this is this part. Yes, this is this part. What is this? W plus t theta intersection k. This is the part. Okay, very good. So in all directions, you chop off, sort of, you can think that you chop off the same volume. And then what you do, you're going to define the body, the part that is always stays dry. This is the dry part. How I'm going to define it? Let me define it carefully. So I'm going to turn the page. So the dry part, I'm going to define this. This is the dry part. I'm going to define this as the intersection of W minus theta t theta, theta in S1. So this is the intersection of half spaces. This is always convex. Always, no matter what, if K is, let me put it like this. So if K is star-shaped, KD is still convex as the intersection of convex sets, of convex subspaces. And the problem, let's now write the problem of Schutt and Werner. We'll write it like this. If KD is lambda K, for some, let's say lambda positive for simplicity here. You can formulate it for any real. Yes, and d, of course, some fixed number 0, 1 you start with. Then does it follow that k is an ellipsoid? In terms of the radial functions, I can write it like this: rho k d. This is lambda rho k. This is the same thing. Again, for convenience, today I'm not going to think about density. I'm going to think about the area. Okay, for me, this is simpler. So I'm going to write delta. This is just d, the area of k. And I'm going to think in terms of delta. So we will think in terms of delta. Okay, very good. So we are going to find delta and lambda. So we will find delta and lambda, they're connected such that I'll write now like this: a k delta. I will write, this is the same notation, only I will put it the index down, lambda k, yes, or rho k delta minus lambda k is 0. You can think like this, but k is not an ellipsoid. This is how I'm going to write. Okay, now let's make a couple of geometric remarks. They are obvious, but nevertheless, let's make them. So if I have a disk, yes, and if I have a smaller disk, let me put it this way, so something like this. So a disk satisfies this problem, satisfies our equation for any delta and lambda. I mean delta and lambda connected. Yes, this is obvious. So if this is my picture, for example, if this is my water, if this is the angle alpha, and I'm going to use this notation today, then this is cosine alpha, and this is sine alpha, yes. And then what I can write here is that if I take cosine alpha multiplied by my ball of radius 1, yes, assume that this is 1, then I have exactly this b delta. And of course, delta could be evaluated precisely, but I don't want to do that. So if you have a disk or a ball in any dimension that satisfies this equation for any parameters. And from now on, for simplicity, I'm going to put lambda is equal to cosine alpha, because our bodies are going to be small perturbations of the Euclidean ball. So our counterexample will be a small perturbation of the Euclidean ball or disk. I'll call this a ball, disk, or whatever you prefer. Okay, so why ellipsoids? Now let's understand why ellipsoids. There are many reasons to this. I will cheat and give you the simplest. So if you have a linear transformation, if T is a linear transformation, non-degenerate linear transformation, yes, so then one can show that T of k delta, this is the same as Tk determinant T. So you change the density and you change the image, and hence if you have this equation of ours, if you have this k delta lambda k, so if you apply T and you apply T here, and what are you going to get? On the left, you're going to get Tk determinant T delta, and on the right, you are going to have Tk. So, and this is an ellipsoid. So ellipsoids are also in. Okay. So now we claim that there is something else that is in. Very good. So I'm going to write things in the following form. I'm going to introduce an auxiliary function, f. This f is going to be dependent on two parameters. I'm write lambda and rho k. Okay. Alpha is going to be from 0 to pi over 2. I mean, I didn't say this, but the intersection I defined before, this dry part could be empty, but I'm not going to use this. We are going to leave, I mean, you will see the densities are going to be small or large, whatever you prefer to call them. And so you're not going to have this problem with emptiness of the dry part. So if you have this auxiliary function, so how I'm going to define this? This is just cosine alpha rho k minus rho k delta. This is how it is defined, and delta is a function of alpha. Okay, very good. So what is our idea? How are we going to construct a counterexample? So how to guess for a counterexample, first of all. So how to guess for a counterexample. What we are going to do at the beginning, this is the question. What we are going to do at the beginning, we are going to linearize this problem, because this map rho k to rho k delta is complicated. This is complicated. And what we are going to do, we are going to linearize this equation. So instead of f alpha rho k, we are going to consider df. Let me put the index down. Yes, I'm going to write this is f alpha rho k. It doesn't really matter. df alpha, I'm going to write here delta rho k. I'm going to explain everything in a moment. And instead of our equation that we have, let me put a different column. Our equation that we want to solve f alpha rho k is 0. Instead of this, I'm going to use the equation d alpha f delta rho is equal to 0. So this is what we want. And this is what we are going to use to guess. Okay, so I'm going to explain what the delta rho k is and everything. And then this equation that I'm going to see here, this equation is going to be much easier. It's going to be a convolution, and it will be very easy to analyze it using the Fourier coefficients. Okay, so let's introduce this delta rho k. What do I mean by delta rho k? If I'm going to write, just a second, please. If I'm going to write delta rho k, I mean that this is rho k1 minus rho k2, where k1, k2 are close to the disk. How close, you will see in a moment precisely, but just close right now. And when I'm going to write delta rho k delta, I'm going to write this, I mean rho k1 delta minus rho k2 delta. This is what I'm going to write, okay? And the claim is that I have this difficult map, rho k to rho k delta. This is hard. So instead, we are going somehow to linearize this. So we are going to have delta rho k going to this some kind of a differential, and this is going to be some kernel k alpha, depending on alpha, convolve with delta rho k. So what I'm going to say, how I'm going to think. I'm going to think, please think that this delta rho k delta, this is exactly the convolution k alpha with delta rho k. Okay, this is the main part. What is k alpha? K alpha is going to be 1 over 2 sine alpha. You will see how it appears. The characteristic function 1 minus alpha. Again, I identify, of course, if I have a disk and if I have an angle. Yes, so I identify the vector. So for me, cosine theta sine theta stupidly is equal to theta. Okay, so I'm not going to bother where I am on the circle or on 0 to pi segment, where 2 pi is equal to 0. Okay, so why the kernel and why this convolution? If you believe for a second that this trick is correct, that this statement is correct, then we are going to use the Fourier coefficient to analyze our differential, and we are going to be good, because what is, at least in the first order, and we are going to smell this counterexample. So in the first order, let's write this. In the first order, assume that our counterexample kind of small perturbation of the Euclidean ball, as I promised. Then I'm going to have this f alpha 1 plus some small perturbation. This is the perturbation. Yes, so I have this is going to be what? This is going to be like in calculus. F alpha 1 plus the differential alpha delta rho plus something that I'm going to neglect for a moment, okay? This is the error and I'm going to neglect it. So what this f alpha of 1? the radial function of the Euclidean ball is identically 1. So of course the ball satisfies our condition. I recall that our f alpha of 1, this is what? This is the cosine alpha for the corresponding alpha, yes, of rho ball minus rho ball delta. And of course this is identically 0, so this part is 0. Yes. And if I want to neglect my arrow, if we neglect the arrow, so if we neglect, okay, just a second, please. If we neglect the error for a moment, then to solve f alpha 1 plus delta rho is equal to 0, this is the same as, I don't want to turn the page on, I'll write it in red. This is the same as to solve, I will write it here, df alpha of delta rho is equal to 0. Again, if I neglect the arrow, this is equal to 0 is the same as this is equal to 0. And this is how we are going to concentrate. So let me formulate the result precisely. So I'm going to formulate now this type of statement precisely. Just a second. So what am I going to say? I'm going to say again that the differential of this, let me write it like, let me write the precise statement. So what I want to say df alpha of delta rho. This is going to be cosine alpha delta rho minus, yes, minus what? Minus the convolution of k alpha with delta rho, where again k alpha, this is 1 over 2 sine alpha, the characteristic function minus alpha alpha. Okay, so this is up to an arrow. Very good. So in particular, we will see in particular, maybe let's see this. In particular, what I'm going to say that this increment of this difference for the floating bodies, yes, for the dry parts, this is about this thing. Yes. So let me formulate this precisely. Again, this is up to an error, but let me formulate this precisely, and then we'll discuss the proof. This is the main part. So lemma, so fix any alpha between 0 and pi over 2 for simplicity. And then there exists a gamma positive constant, and there exists this L positive constant. Gamma is small, this is small. Yes, such that if K1, K2 are two star-shaped bodies, yes, in R2, yes, with the continuous radial functions rho K1, rho K2, such that, let me write it like this, the norm, they're close to the unit disk, yes, less or equal than gamma, J is 1 and 2. Then what we are going to get, now I am going to formulate precisely the statement, what I'm going to use, yes, then I'm going to have defense. So the difference, this is the increment 1, well, let me write it honestly. Yes, so I want rho K1 delta of theta minus rho K2 delta of theta minus 1 over 2 sine alpha, and integral theta minus alpha theta plus alpha, and here rho 1, let's say, of tau, well, rho K1 of tau minus rho K2 of tau d tau. I close the absolute value, and this does not exceed this square root of gamma rho 1 minus rho 2, let's say in L2. Okay, this could be done pointwise. This is kind of almost differentiability. This is not really true differentiability because your both bodies are close to the disk. Okay, if they are far, we may not prove this. And this is very, very important, an important remark, a very important remark. Very important remark. We work with the C, with the space of continuous functions. This is very important because if you want to prove a similar statement to some kind of smooth Banach space, let me put it this way, if you want to deal somehow with the convexity, then it's going to be hard. I don't know how to do it. And I didn't say the most important thing at the beginning, but I wrote this in the abstract. So, okay, but let me, I don't want to jump. So I'll say this at the end. So what I'm trying to say is that this is 0 for us, neglected, this is 0. So if this is of the order gamma, yes, then this is a high order term, so we can neglect it. So this is exactly what I drew here. This is delta rho of k delta, and this is exactly this kernel convolved with delta rho. This is what I wrote before, and they are equal. Let me explain why this is true, and then I'll explain how to use it. So if let me introduce the support function. Okay, I'm not going to prove this precisely because this is long and difficult. I want to give you the idea why you have this convolution. This is the most important thing. So this dry part is somehow you should think about in the first approximation the convolution with the kernel. So the support function of a convex body K, HK, is introduced as what? In the direction X, let's say. So if this is your body, convex body, think K is convex. So this is your direction X. And so what you do, you walk till you touch the horizon here somewhere. Yes, this is the dual norm if you want, if the body is origin symmetric, which is not the case here. This is HK of X. Okay, so I will write this precisely. This is maximum of X dot Y over all Y and K. So what I'm going to show you, I'm not going to show you this thing that what I promised. Let me shorthand this. I'm not going to show you this. What I'm going to show you is this. Again, I put this in quotation marks. I mean, I omit the error. Yes. So this is easier, but this is the idea. This is the idea. This is where it came from. Again, I emphasize that when we write our original problem, this is lambda k is k delta. Yes. When we write our original problem, this is whatever we want, yes? But this is convex. So if you find a counterexample in the space of star-shaped bodies, the resulting function is going to be convex automatically, and I mean not function, the body. So this is exactly the point where you win here in this situation. Because this kind of quasi-differentiability, what I had before, this lemma, is very convenient to prove in the space of continuous function without convexity. And it is going to be very convenient to use it in the implicit function theorem we are going to use, or the Banach fixed point theorem, whatever you call it. Yes, and if you use some kind of smoothness, then it's not clear how to obtain a similar result. And this is the most important kind of remark here, as I mentioned before. Okay, very good. So let's try to prove this heuristically, why we have this kernel. And if we have it, of course, we can analyze everything using the Fourier coefficients. No, let's draw. So our body is going to be a small perturbation of the ball. So no, let's try something like this. This is the ball. This is some kind of a smaller ball. Let's draw it like this. And so this is our water somehow. Yes, this is. This angle is going to be cosine alpha. Sorry, this is cosine alpha. And this is sine alpha. Yes. Very good. So assume that we make a small perturbation. Okay, something like, of course, the perturbation could go something like this. This is going to be your body. Yes. So this is the thing. Yes, but you don't want to do it this way. Yes, I don't want to do it like this. I want to do it a little bit. just for simplicity. So that just to indicate the idea. So there is some kind of so there is some kind of let me draw it again. I apologize. Something like this. So this is another circle. Then this is my cosine alpha. I apologize. Just a second. Let me close the door. Sorry. So this is cosine alpha. This is sine alpha. This is alpha. So this is my body B cosine alpha of radius alpha. This is my body B1, the disk. This is the origin. So this is my water. And this is my underwater part. I just draw it this way because I told you I'm going to change the horizon. Very good. So I know that this is delta. Yes. So assume that I have a small perturbation, something like this. Then what is going to happen? Then also here is going to be something like this. Yes. Think that this is convex. In the picture, this is not convex, but this is convex. Okay, very good. So I want to perturb my water. So this is my water for the ball. And I know that this is delta. So I want to perturb my body. So this is a small perturbation. And I know that the new water is going to be like in the picture. The new water is going to be here. This is water for the body. Yes, because I also want this now, because I have here something extra. So I want this also to be delta. They're both delta. But now what is delta H? Delta H is exactly the distance here between these two waters. So this delta H is the distance between the waters. But what is this distance? This distance is exactly, please look at this rectangle. If I draw this rectangle here, neglect the arrows, they are going to be infinitesimally small. If I have this arrow, if I have this rectangle, like I draw here, this is the rectangle, where here also have this alpha, yes, and here alpha, in this cone. And this rectangle, so I can write this, my delta H is exactly the area of the rectangle divided by 2 sine alpha, yes, by 2 sine alpha, because this is sine alpha and this is sine alpha. So basically what we use is that the height of the rectangle is the area of the rectangle divided by the length of the base. Very good, but by Archimedes, yes, we know precisely that the area of this rectangle, how much your water should go up, is exactly the area here. So in fact, I can write here, let me write it here, the delta H is, let me write it like this, the area of this perturbation divided by 2 sine alpha. Yes, again, I'm writing equal, this is up to an error, and the error is going to be accumulated here, but don't care, this is infinitesimally small. This will be of the order very, very, very tiny. So one can show. So what I'm trying to say, precisely if this is epsilon squared, yes, so up to a constant. So what I'm trying to say now, let me erase this a little bit here. So what I'm trying to say is that I'm going to write delta H, and now I'm going to find this area of the perturbed part. What is the area of the perturbed part? I have my cone minus alpha alpha, and I have to integrate. Imagine that you have a general perturbation, yes, and I want to find this thing. So what is this? This is exactly the area of the perturbed guy minus the area of the ball. So this is what I'm going to do. So this is the area of the perturbed person, yes, minus the area of the disk divided in the cone. Yes, everything is, let me write it precisely, more precisely. This is in the cone alpha. Let me write this. Okay, now there are some two angles. Somehow I apologize, but you understand what I'm talking about. Area of the disk, this here, intersection C alpha, and I divide by 2 sine alpha. So if I pass to polar coordinates, then I just have to find this piece. I have to pass to polar coordinates. If I pass to polar coordinates, I don't want to change the page. So if I pass to polar coordinates, then the numerator here, this is just going to be what? This is, I can write it here. So this is going to be 1 over 2 sine alpha, because this is our denominator. If this vector, let's say this is the vector theta, then this is the cone C alpha of theta. Yes, so then what I have to do, I have to write that this is an integral theta minus alpha, theta plus alpha, because I have to integrate in the cone. And here I have to put this increment rho k squared in polar coordinates of tau minus 1 d tau. Well, I mean, I use one body as k and another body I use as the disk. Okay, very good. So now if you linearize this thing, so if you linearize this expression, I'll write it again in the next page. This is your numerator, and this is the convolution we were looking for. Yes. So now, if let me turn the page. So if I have now again my expression 2 sine alpha, theta minus alpha, theta plus alpha, and here I have rho chi squared tau minus 1, and of course I lost one more 2, because the base was 2 sine alpha, and I lost 2 when I passed to polar coordinates, but up to the higher order terms, yes, rho k is 1 plus phi, where this is a small perturbation, yes, small function, very smooth. So then this is going to be like 2 rho up to higher order terms. So this 2 is going to be cancelled with this, and this is exactly what I promised you, k alpha convolved with delta rho. So this is the heuristical argument. This is the most important thing. And now, if you believe in this, I hope you do, then now I'm going to show you how we are going to. So I promised you that instead of f alpha rho k0, so instead of this, we will study df alpha of delta rho k is equal to 0 in the first approximation. And today I'm going to work only in the first approximation. I'm not going to have enough time to explain you the rest, but the idea will be indicated. Yes, so this is much easier because this is a convolution operator. This is a convolution operator, and we can use Fourier coefficients. The Fourier coefficients come into play. Yes, come into play. So if I want come into play, I am going to write them like this, the Fourier coefficient. So if I have any function, I recall the Fourier coefficient, but I mean, but what I'm trying to say is that how our differential looks. Our differential looks like this, like I promised. This is equal to 0. This is how it looks. So if I apply the Fourier coefficients, yes. So if I write df alpha, well, at delta rho, let me omit k. Okay. If I put the Fourier coefficient of this is the Fourier coefficient of the kernel times the Fourier coefficient of delta rho, and you can precisely compute the Fourier coefficient of the kernel. Yes, k alpha of this thing. Yes. So what is going to be here? K alpha. Yes, I mean this. I have to put here the tilde. Let me, you know what? Let me indicate this. Let me use a different letter, because k alpha I used for the k alpha I used to explain how this fluid dry part is linearized. But here, let me write it's maybe h alpha. Okay, so then I have here h alpha. And what is h? H alpha convolved with delta rho k. This is going to be cosine alpha delta rho k minus k alpha we had before delta rho k. So if I have the Fourier coefficient of this h alpha L, this is cosine alpha minus, because this is the identity operator. And here I have, if I compute everything, I'm going to have sine of L alpha divided by L sine alpha. Yes, this is the, and observe that if for any alpha H alpha of 2, the second Fourier coefficient is identically 0, because it amounts to what? To say that sine of 2 alpha is 2 sine alpha cosine alpha. And this is another indication of the fact that the ellipsoids are in the game. Yes, for any alpha. Okay, very good. So now what is the idea? The idea is that we are going to somehow change the second Fourier coefficient to the fifth Fourier coefficient, and you are going to see why this is going to happen. So heuristically, again, I will turn the page on. I want, what do we want? We want this again, I will recall. I want to solve this. So for us, if I want to guess, does there exist alpha such that this Fourier coefficient of alpha L is 0 for some L not 2. This is the question. Of course, if L is 0, this is easy, yes, but I want some not trivial, yes. Okay, not 0. Okay, how are we going to do that? And this is also the most important part. So I claim that this exists, yes? Claim yes. It does, and this is the most important part. If we finish this and we are done, let's do it. So let's just draw this multiplier. So we know, what do we know? We know that H, let's call this Fourier coefficient, well, it doesn't matter. Let's call this H alpha of L of 2. This is identically 0 for any alpha. So let's consider the difference of two multipliers. Let's consider Fourier coefficient 5 minus Fourier coefficient of 2. Okay. Then cosines are cancelled. Cosines are cancelled. So, and what we are going to get? We are going to get, according to the multiplier I wrote, what we are going to get, remind me please, so sine of 2 alpha divided by 2 sine alpha minus sine of 5 alpha divided by 5 sine alpha. And I'm going to write this in the integral form. I'm going to write this as 1 over sine alpha, and here an integral from 0 to alpha, and here I will write cosine of 2 tau minus sine of 2 tau d tau. So what I'm going to claim, let's call this, I don't know, let's call this some f of alpha, okay? Let's call this like this. So I'm going to claim that there exists some alpha naught such that this integral f of alpha naught is 0. And hence, because this guy is identically 0, we are going to show hence that there exists alpha naught such that H alpha naught, the fifth Fourier coefficient, is 0. And this is going to be a strong indication that there is a counterexample. Okay, let's understand this. This is just the intermediate value theorem. Okay, so let me turn the page on, and I'll explain because I want to make a bigger picture. So I have something like this. This is my axis. I'm going to draw sines and cosines. Okay, so again, I have the difference of what? Of sines there, yes? Of cosines. I have the difference of cosines, yes? Yes, I have the difference of cosine here and here. So I'm going to draw, I wrote bad thing, 5 should be there, yes? 5. Just a second, again, let's be careful. Sine, this is minus, this is plus. No, 5 should be here and 2 should be here. 5 is here and 2 is here, but it doesn't matter, you will see. Okay, very good. What I'm going to claim, I'm going to claim that for alpha small, this f of alpha is going to be negative, and for alpha large means close to pi over 2. Yes? F alpha is going to be positive, and hence by the intermediate value theorem, hence there exists alpha naught such that f of alpha naught is 0. This is what I'm going to claim. Now let's make a picture. Let's look at this multiplier, cosine 5 tau minus sine 2 tau, and let's just integrate it from 0 to alpha. So I have this thing. So I have this pi over 4, and I have this pi over 2, and I have this 1, this is 0, and I have my function, this is cosine of 2 tau. Okay, very good. So now I want to draw like cosine of 5 tau. Let's draw this something like this. I mean, please be patient with my art ability, something like this. So this is cosine of 5 tau. Very good. So let's look what's going on. If I'm here, let's make it, well, green. If I'm here, alpha is small. Then what is going to happen? Then you see that cosine of 2 tau is larger than cosine of 5 tau. Hence our integral, hence our multiplier is going to be positive. Hence, an integral from 0 to alpha, the denominator is always positive. Yes, cosine of 2 tau minus cosine of 5 tau. It doesn't really matter if I mix the minus or plus, doesn't really matter for us. This is positive. But what happens if alpha is large? Now let's understand what if alpha is large. Large. So close pi over 2. So what if we are here? Let's understand. So cosine is going to, the integral from 0 to here is going to be almost dead, yes, for the cosine, because this is plus and this is minus. But what is going to happen for cosine of 5? This is plus, this is minus, this is minus, this is plus, and you have the extra plus. And this is exactly why for large things, this second integral of 5 over 2 is going to win. And you're going to have a negative value, yes? And this is exactly how you smell that. So there exists this alpha naught such that this Fourier coefficient number 5 is 0. Okay, so this means that you had this function. So we got the counterexample. I have 4 minutes. I will indicate now what to do next, and that's it. So you have again, so what you had this disk. This is the disk. And now you're going to perturb it. You're going to have a small number s times this cosine of 5 tau. And what you know that df alpha of 1 plus s cosine, well, even without 1, you know that this guy on the fifth harmonic is 0 for alpha naught. Hence, in the first approximation, you solve the problem because you have f alpha naught 1 plus s cosine 5 tau. Yes. This is by the differentiation formula plus df alpha. This is identically 0 for any alpha, d alpha s cosine theta, and plus the guy you're going to neglect for a moment. This is identically 0, and hence you solve this in the first order you solved it. We solved it. Unfortunately, now the game begins. Unfortunately, if you want to work, now you have to deal with this error, yes, and then you're going to use the implicit function theorem. Let me just say these words. I don't have time to explain this, but the main part I explain you. So now the implicit function theorem. Implicit function theorem. And this is very well described in the book of Havin Yoriki. Yes, so this is the method was applied by Kargaev and by Kantarovich, Havin and his school, and then by Crandall and Rabinovitz. They call this the bifurcation theorem, etc. So this is a very well-known technique. So you're going to create a certain process. So far our perturbation looks like this, but you're going to add this phi somehow. And what you're going to do, you are going to get phi such that our original s, just a second, s, our original equation cosine 5 tau plus phi is 0. And this will be for alpha close to alpha naught, because you will need to apply the intermediate value theorem again. So this implicit function theorem here is going, or the Banach fixed point theorem, whatever you call it. If you want to apply it, you have to choose the Banach space. So choose the Banach space. And the Banach space I'm going to choose, let me indicate, like I'll put it first C5. So C5, this is going to be the space, well, in 0 to pi. I have 1 minute, and 0 to pi, this is the space of even continuous 2 pi periodic functions. Well, in fact, 2 pi over 5 periodic functions. 5, as I showed you, is not really important. Any for k plus 1 will do, but let's stick to 5. So this is the Banach space you're going. I mean, this is the Banach space you're going to work with. But unfortunately, if you run through this implicit function theory business, in the classical theorem, the differential should be not degenerated. But here it is degenerated because on cosines, as we saw, it dies. So in fact, you have to introduce another Banach space where you're going to work with. And this space is all these functions, you have to be orthogonal to cosine of 5 theta. So you have a subspace of C5, and this is the space you're going to work with. And then if you run this procedure, and I don't have time for this, yes, if you run this procedure, you're going to figure out the function. Let me write down how the function is going to look, your counterexample, and I will skip the details. Yes, so just a second, please. This is how your function is going to look. So rho, let's say of theta. This is going to be some rho naught. This is going to be 1 plus something small, some O small of something. And then what you're going to, let's call it S, okay? And plus S, this is your perturbation cosine 5 theta, plus going to be rho 10 cosine of 10 theta, because of the symmetry, plus rho 15 of cosine of 15 theta, and plus etc. So the picture is like this. This is some kind of a pentagon. Yes, this is the origin. This is your theta. This is how the function is going to look. And all of these coefficients, rho, whatever, 5L, L greater or equal than 2, they're all tiny. They're all O of S of this perturbation. S is tiny and they're even tinier. So this is how you're going to get this. And so what you're going to do, you're going to plug it into your equation, F alpha of rho. You're going to plug it into your equation, and you're going to get something. And then using the intermediate value theorem, you're going to get 0 here. You're going to find the specific angle. I mean, you're going to show that everything depends smoothly, continuously on alpha, and the fixed point depends continuously on alpha, and then you can choose it. But I don't have time for this, and I hope I explained you the idea. Thank you very much. One last thing. I'm sorry. Of course, this is very important. I forgot the most important thing. This is a joint work with Maria Alfonseca, Fyodor Nazarov. This is a long project, like probably since 2007, 18 years. Fyodor Nazarov, Alina Stanku, and Vlad Yaskin. Yes. She is in North Dakota, Fedi is here, Alina Stanku in Montreal, and Vlad is in Edmonton. Okay, thank you very much.
Well, thank you for a very important, interesting talk. And we have time for questions. If there are questions, please raise hands. Maybe while I have some small question, I'm wondering, because knowing your research, I would expect kind of Radon transform integrals type like this, but instead...
Yes, you need this, Alyosha. Yes, you need this, but in higher dimensions. Yes. I
So
mean, if you run this descent,
case,
it will show up there. Yes, and starting from dimension 3, yes.
So in this case, you'll have same calculations, but using Radon transform.
Yeah, I mean, okay, the same calculation you're going to use here. You're going to use the same calculation, but using the spherical cap transform. Yes, but then it depends on the problem. If you consider slightly different problem, you will need the Radon transform. Okay, so here this alpha in R3, this is going to be the spherical cap. And you're going to, if this is a cap, I don't know how to call this, sec alpha, this is theta. You're going to use this characteristic function of the cap. This is almost like the Radon transform, you know. Yes, this is the operator. But the radon transform, I mean, okay, I just don't want to have time for this. Let me formulate you the problem, which is very close to this. And if, in fact, I think that they're kind of similar. Yes, but here, observe, I didn't mention this, but it's clear. The body we constructed is not origin symmetric, okay?
Mhm.
Because you have this 1 plus, you know for sure, 1 plus s cosine 5 theta plus some rubbish. This indicates that this is not origin symmetric. So if you want your spherical radon transform, you want to work with bodies that are origin symmetric because of the kernel. And in this case, you have the following problem. If you have a convex body, this is called Buzman-Petit problem number 5. It's open. Buzman-Petit problem number 5. Well, 5. Let me write it like this. So this is origin symmetric. K is origin symmetric. You have this direction theta, and you have this subspace theta pure orthogonal to your theta, and you have this section. Okay, then you bring this hyperplane up. Think about the three-dimensional case. You touch it somewhere. So this is your support function. Okay, then the question is the following. If the area of this K intersection theta perp, the area of this person, times this height, times the support function, hk of theta, if this is identically constant, independent of theta, then does it follow that K is an ellipsoid? This is an open question. And here you have precisely the radon transform. This question is very similar if you start writing the proof, like local, if you're close to the disk, if you start writing the proof here, then the radon transform appear here, the spherical radon transform, and everything will be literally the same. I mean, I didn't speak about the positive part, but the logic will be the same. Let me put it this way. And so here, basically, these two problems are similar in a way that for the Buzman-PT5, you need the spherical radon transform, what you ask. And for the floating body, homothety, the stain of Schutt and Werner, you need the convolution with the spherical cap. But they are very similar, because if you, for example, if you have if your alpha is huge, pi over 2, yes, or 0, whatever you define, it doesn't matter. Yes, if you have half of the sphere, then the derivative of this semi-spherical radon transform is the spherical radon transform. Yes, so this is kind of an integral of what you ask.
Okay.
Yes, but I mean, but these problems are all the same here. Yeah, somehow.
Yeah, it can be understandable, but I understand that this kind of hard calculations and hard problem to solve. And these problems, maybe you tell us where we can find the description of these problems in the literature, like for general.
Yeah. I mean, the description. No. Oh, it's a good question. We have an expository paper about floating things. I can send you the details on. There is an expository paper by Maria Alfonseca, Alina Stanku, and Vlad Yaskin, and myself. And there is another expository paper. Oh, Alyosha, give me 1 second. I will give you the precise titles, okay? Because I don't remember like by heart. In just a second. Okay, this paper is called on flotation, stability, and related questions. And a survey. This is how it is called. And no, first of all, I can send you. You can find it on my webpage, but it's going to appear in this BOIAE Society Math Studies. Yes, this is volume 32, Springer, Berlin. Yes, and another paper Another paper is with Fedya Nazarov and Vlad Yaskin. This is another paper, how it is called. I will tell you also expository. Just a second. Let me see where I see here on. No. If I have it here, just a second. Yes, I have it here. Analysis and geometry. Near the unit ball. Proofs, counterexamples, and open questions. Proofs, counterexamples, and open questions. And this is just a second. This is harmonic analysis and convexity. Harmonic analysis and convexity. Just a second. I will tell you this is how it is called. Now, this is also Maria Fonseca. I missed you. I apologize. Okay, so just a second. Where is the? This is going to be advances in analysis and geometry. Again, you can find it on my webpage. This is 9. This I don't know how to pronounce. The grew YTR Berlin 2023 pages. I'll give you pages in a moment. 445, 468. So these are the references where you can find many things there. Yes, the first reference is kind of written for students. Yes, and the second is exactly already deeper for researchers, explaining this technique, etc. Yes.
Okay. But I would guess that stabilization or stability, you mentioned there, stabilization or stability is a very important issue in very practical issue. But it's still very complicated.
Yes.
Because your shape of body
nothing is known there.
It's not always good, right? So how to?
Yes. No. This is a difficult stuff.
I have no idea how to do this.
The reason I didn't choose to speak about those stuff is exactly not much is known there, and even simpler questions are open. The simplest question I'm asking, let me just write for everyone. This is the simplest question. I don't know any person who answered positively. I mean, correctly. So you have a triangle. What could be easier? I don't know if you see what I'm writing.
Yes.
You have a triangle. I mean, a regular triangle. Yes, 60 degrees. And you put it in water. Triangle of some density. So if you want physical experiment, you have this triangle, you have a prism. Triangular prism, yes? And then you just, before you study stability, find the directions in which this triangular prism floats in equilibrium. So a triangle floats in equilibrium. Before you enter stability, stability is harder. But before, easy question, what it means floats in equilibrium? It means, no, for example, in my picture here, this is the center of mass of my triangle. This is the center of mass of the underwater part. I take these 2 points, and they're connected with a line, and I have here 90 degrees. Then I call it stable. For example, if I have a triangle like this, and the water is like this, then it's stable. The center of mass of the triangle here, the center of mass of the underwater part here. I draw. I have 90 degrees. It means it floats in equilibrium. Okay? So, for example, also if I put my triangle like this, ideally, this is water. Again, the center of mass here, the center of mass of the underwater part here. I have here 90 degrees. But for example, if I have something slightly different, yes, it's like this, yes, and if I put it in water, Yes, this is the center of mass here, the center of mass here. You see it's not going to be 90 degrees, not 90 degrees. So it's not stable. Not floats, and it does not float in equilibrium. Question: if I am giving you the fixed density, you have a triangle. Question: given a triangle, given a density.
I don't actually see what you write.
You
Maybe
don't
it's
see why?
because no new symbols appear
Huh.
since.
Okay, but I will tell you out loud. You don't need to see. How many directions of equilibrium does this prism have?
Okay, now it's appeared. Okay.
It appeared. It appeared. So
Yeah.
so how many, given the density, how many directions of equilibrium does this triangle have? I mean, I formulate this in this kind of simple terms manner. Yes, of course, you need to create a prism and put it in water, but I don't want. Think two-dimensional. How many? Every person I know says, take this one direction, take this another direction, two. You have three vertices, 6 directions, and you are done. Everybody says this, but no. This is a home assignment, very hard problem. For some densities, there are 12 directions on equilibrium. Unbelievable. So even for a triangle, this is difficult. I mean, and this was solved by Davidov and Masbornik. This is in 19th century. It was solved, but the solution is not trivial. It's a high school solution. At the moment I'll give you a hint, you will solve it, but this hint is very hard to solve, and even people like Erdos and many others, they try to invent these difficult solutions, etc. There is a solution to this, and this is not trivial. This is even before we enter stability. Okay, just we want to suspect where to look before we enter this, and stability is instant death. Very hard questions.
Okay, thank you. Thank you for a very nice explanation. Maybe more questions? I don't see hands. Well, if no more questions, then let's thank speaker for very nice presentation.
Okay, thank you very much for the invitation.
Thank you very much, Professor Ryabogin, for very interesting talk.